This is continuing on from the previous two talks. I'm going to discuss a different aspect about gravity, specifically black holes. But what I want to discuss about is how the existence of black holes themselves tell us that we don't understand something about gravity. And you'll see why that is true as we go along. So the overview of my talk will be I'll discuss about black holes, and then I'll tell you why the black holes aren't black at all. Maybe they're not holes either. And then I'll discuss about an idea called the holographic world. And so let me begin with black holes. And black holes in some sense are beautiful objects in gravitational theories, in a sense that I will describe, and they're somehow nature's laboratories, theoretical laboratories for gravity. In other words, the nature of black holes really tells us something fundamental about our gravitational theories. And if we do attempt to try and modify gravity, then we will also modify the features of black holes. And so it's very important to understand what happens when we do that. So you've heard in previous talks in this series that the mysteries of dark energy and dark matter have forced us to question both Newton and Einstein's pictures of gravity. So the existence of dark matter questions whether we should view whether Newtonian gravity is the appropriate force at, Einstein's gravity is the appropriate force at galactic scales. And dark energy, this even bigger problem, the fact that we don't know what 70% of the makeup of the energy density of the universe is and why the universe is accelerating, has led to a fundamental question of whether Einstein's theory, the full Einstein's theory of relativity, is really the correct picture of gravity. But I actually want to start with something that is a clear prediction of Einstein's theory of relativity, and probably one of its most spectacular predictions, which is the existence of black holes. And it wasn't really Einstein himself that made this prediction. In fact, so Einstein published his full theory of general relativity in 1915, and only a couple of months later, he received a letter from the Russian front. Of course, this was the First World War. And somebody, a professor named Karl Schwarzschild, who was fighting on the Russian front, in his spare time decided to solve Einstein's equations of general relativity. And he sent a letter to Einstein, and he pointed out that Einstein had tried to find the solution describing a star, a spherically symmetric solution describing the external space-time geometry of a star. And he made some approximations, and he hadn't done it quite right. And Schwarzschild, in his spare time whilst fighting on the Russian front, sent him the correct answer. And as you see, the quote from Einstein there, he did not expect that one could actually formulate the exact solution of the problem. And Schwarzschild found that solution. And that solution looks like this. Don't worry too much about the details. I'll just write it there just to show you that we really can write down a black hole in simple form, in one line. That is a black hole geometry that describes the space-time of a black hole. This describes a space-time geometry where t here is the time, and r is the radial coordinate, and theta and phi are the angular coordinates. But don't worry too much about the details of that. The key point is that he found this particular solution. The remarkable thing he found about this solution, which is why we call it a black hole now, is that it's the correct solution describes the space-time external to a star. But if you imagine changing the size of the star, once the radius of the star gets down to some special value, which is determined by the mass of the star, the Newton's gravitational coupling constant, and the speed of light, this particular combination, which we now call the Schwarzschild radius, then it's no longer possible for light emitted by the star to reach infinity. In other words, to reach us. We will simply not see anything. And that's what we call a black hole. And so in some sense, we can't really draw a nice picture of a black hole, but this is a sort of this is a theoretical model of a black hole. This is all the lensing effects, gravitational lensing effects due to the black hole, and this just black thing is just supposed to represent the black hole at some particular radius with the Schwarzschild radius. And so anything that's inside that radius, we simply wouldn't be able to see. The solution also contains a weird thing, which is what we'll call a singularity. At r equals 0, it blows up, and I'll discuss that a little more in a second. But what does all this mean? So let's think about escape velocity. Let's suppose we want to send a rocket to the moon. that rocket has to escape the Earth's gravitational field. And there's a minimum velocity that you need to send the rocket up so that it'll be able to get out of the Earth's gravitational field, because as the rocket goes up, gravity will pull it down and slow it down and slow it down. And the problem is, if you do that with an apple, you throw it up, gravity wins, and it'll always drop down back before it'll escape. So there's no way we're going to be able to throw an apple using our own arms all the way to the moon. But we build rockets that start off fast enough, and the fast enough corresponds to about 7 miles per second, or 11 kilometers per second. And that's called the escape velocity. It's the velocity we need to escape the Earth's gravitational field. Now, let's imagine the same thing for a star. Suppose you sat on the surface of the star. There's some escape velocity in order to escape the gravitational field of a star. And as the star gets smaller and you're still on the surface, then gravity gets stronger, or as the mass gets bigger, the gravity gets stronger, and you need a bigger and bigger escape velocity. And a black hole is the object, is essentially a kind of star that has reached the point where the escape velocity is more than the speed of light to escape. So that light itself cannot escape the gravitational field of that star, if we can call it a star. And that's what a black hole is. And it turns out that this idea was invented or theorized in 1783. It was originally called dark stars, so that's really what we should call it, but people forgot about this. And John Michell, a Cambridge-educated English country parson, I think he went on to work as a professor at Cambridge after that, but he presented a paper in front of the Royal Society, which was the place to present papers in those days. And this was his paper, and it was written in a terrible 18th century style that you wouldn't know what it was about. But if you just read the first lines, it says, if there should really exist in nature any bodies whose density is not less than that of the sun, and whose diameter are more than 500 times the diameter of the sun, then since light could not arrive at us, and that's the key point, which he hasn't explained why light doesn't arrive, but he means that light doesn't arrive at us because of the gravitational field. And he goes on in that paper to basically theorize the whole picture of black holes using Newtonian gravity. And in fact, you can compute the correct Schwarzschild radius using only Newtonian gravity. It's also, so black holes were a feature also of Newton's theory of gravity, as Michell discovered. And this idea was also come up with independently a few years later by the famous French mathematician Laplace. Laplace is much better known, so he tends to get the attribution for this. But Michell was actually the first. And that's the idea of a black hole. Now, this, of course, people didn't think about this for a long time. Now, let's push forward in history and get to the date of September the 1st, 1939. Now, several things happened on that day of different importance. The most significant one is that Hitler invaded Poland, and that was the beginning of the Second World War. On that same day, Niels Bohr and John Wheeler, very famous physicists, published an account in the Physical Review on the mechanism of nuclear fission. And of course, that became very important because that was basically a theoretical understanding of how the nucleus could, how a nucleus of an atom could split. And of course, that played a significant role in the building of the atomic bomb. And it's somewhat ironic that that paper was published on the same day. But another paper was published on that day, which actually plays a more important role for this talk. And again, ironically, the author of this paper was J. Robert Oppenheimer, who would go on to lead the Manhattan Project. And essentially, this was the only paper he wrote on, or the last paper he wrote on this idea of the gravitational collapse of stars before he went on to other things. But it was a very significant paper, probably his best piece of scientific work outside of, it's probably the best piece of scientific work. And it gave an account with his collaborator Hartland Schneider of how a star, which has burned all its nuclear fuel, so there's no internal pressure to stop the gravitational collapse. And it gave an account, he basically solved Einstein's equations to describe how the star would collapse. And he showed that the collapse, they both showed that the collapse would eventually always form Schwarzschild's solution, the one that Schwarzschild had found in 1916. And this paper was completely ignored for many years. And most people thought it was completely irrelevant because the solution had this singularity. which is the fact that it became ill-defined at radius 0. This is a picture of the black hole here. There's a star collapsing, then it collapses, then it forms a horizon, which is this, the Schwarzschild radius, and then a singularity. And it was neglected until the mid-1960s, when astronomers started discovering strange new objects like quasars that had strong gravitational fields. The quasar was this strange, highly energetic thing that emitted lots of radio waves. And people started thinking again about this black hole. Maybe quasars have something to do with black holes. And it was at that time period that John Wheeler coined the term black hole. And then there was an important theoretical development that Stephen Hawking and Roger Penrose proved that general relativity necessarily implied the formation of singularities, the singularities of black holes in our future. And the significance of that is that they basically show that Einstein's theory of relativity, the black holes were not some weird special solution that people had thought about Oppenheimer-Schneider's solution, but they were the inevitable end product of gravitational collapse. They had to arise, and that was probably, that's the work that brought Hawking and Penrose to fame. Now, around that time, there were great theoretical developments, and one of the things that they showed is that there is a uniqueness theorem, that a black hole is completely specified by only 3 parameters: its total mass, its electrical charge, and its angular momentum. And every black hole with the same mass, charge, and angular momentum looks exactly the same. And that's called a uniqueness theorem. There's no fuzziness in it. Every black hole with the same mass and charge and angular momentum looks exactly the same. And John Wheeler referred to this as basically the no-hair conjecture. The picture was that you couldn't imagine hair on a black hole. You could imagine hair sticking out, because if you had hair on, you couldn't just describe that by the total mass, the charge, and it has structure, internal structure. But a black hole doesn't have that. A black hole is completely specified by its mass, its charge, and its angular momentum. So you can't put hair on a black hole. And this is amazing property because it makes black holes sound like elementary particles. Right? Elementary particles like the electrons and the quarks and so on, they're just specified by their mass, their spin, the electric charge, and then their charge under nuclear forces. So it's in this sense that black holes are these remarkably perfect objects. Every black hole of a given mass, given charge, and a given angular momentum looks identical with no corrections, no fuzz, nothing, no perturbations that you can put on that. So these remarkable properties of black holes really point to something deeper about the nature of gravity. So what we've seen is that the theorems of Hawking and Penrose prove that general relativity always leads to these singularities, like the singularities that are inside a black hole. The collapse of matter will always produce a black hole. Oppenheimer and Schneider's solution was not just a special solution, but was essentially a characteristic of the generic feature. And black holes are somehow these perfect objects which are just as perfect as elementary particles. We only need 3 parameters to specify what a black hole looks like. And so these are the properties that make us think that we need to understand these aspects better. And if we understand what a black hole really is, then we will understand something more fundamental about what gravity is.
If black holes are the absence of gravity, how can they be eating up parts of the universe?
It's not really that black holes are the absence of gravity. They're actually very strong gravitational fields. But they're so strong, they're pulling all the matter in, so that externally, you don't see anything. You don't see any special structure of the black hole. But the black hole itself is very strong gravitational field. So it's not the absence of gravity. It's actually very, very, very strong gravity.
Yesterday, the New York Times had a nice article to explain the Nobel Prize in physics about how the Higgs field gives mass to things. How does it give mass to black holes?
So the black hole is an endpoint of gravitational collapse. So the mass, the energy out of which it's built is conserved. So it starts out, if you imagine a star, you start out a star with some mass. That has mass because it's built out of electrons and protons and neutrons. The proton and neutrons are built out of quarks and so on. Now, the mass of many, it's actually not quite true that the Higgs gives everything mass. So in fact, protons and neutrons, most of the mass doesn't come from the mass of the quarks. So the Higgs field gives mass to the quarks, but the mass of the protons and neutrons also includes, because of Einstein's E equals mc squared, it also includes the interaction energy. So all that energy, all that mass is what's incorporated in the mass of the original star. When the star collapses, the total mass of the system is conserved. So the mass of the black hole ends up being the mass of the original system. But what's weird about it is that every black hole looks the same, and so it's just specified by that total mass.
Now, this may seem kind of silly, but I'm envisioning a black hole as being, I can take some snow, and I can squish it together and make a pretty solid piece of ice. Are you saying that the inside of a black hole is likely to be a solid mass per se, or is it something different?
So the truth is we don't really know, because so here's our picture of a black hole, and this is the standard textbook story. So here at r equals 2m, that's the Schwarzschild radius. That's the radius at which, if anything is at there, gravity is so strong that, that light cannot escape from that point. And that's the horizon of the black hole, which is at the Schwarzschild radius. But the standard picture is that as matter falls in, across the horizon, nothing special happens, actually. So if you were falling into a black hole and you hit the horizon of the black hole, you just carry on going. And you'd fall all the way to the singularity. And so if you think of the star as being made of lots of particles, each of those particles just falls in, and they all collapse and form and hit the singularity. So from an external point of view, we can't see inside the black hole. We can't see beyond the horizon. Nevertheless, the standard picture is that it's not a solid object of that size, but rather that all the matter collapses down to the singularity. And if we could go inside the black hole, then what we would find is that it would essentially be empty, and all the matter of the original star would somehow be located at the singularity.
Yes, and that singularity, from what you're saying, would have to be a solid mass at that level.
Yes. Maybe. We don't know what that singularity is. We don't know what happens there.
So it may not be.
That's right. So this is one of the things. Einstein's theory of relativity simply breaks down at that point. So this is one of the things we know we need to modify our understanding. We have absolutely no idea what happens at that singularity.
With regard to the 18th century John Michell view of dark stars, how did they know that gravity actually affected light, or were they just assuming that?
They assumed so, and in those days, of course, people didn't quite know whether light was particles or waves and so on, and so depending on who you spoke to, you would get a different answer. But I think Michell was of the perspective that light was a particle, and he simply assumed that that like everything, particles, every particle is affected by gravity in the same way, right? Because the acceleration is independent of the mass. So he didn't know what the mass of light was, but you don't need to know the mass of the light to know that if light is a particle, it would be affected by gravity. And ironically, in some sense, that was the right answer, although the calculation wasn't correct. Okay, so let me move on to the second part then. So the second part is that black holes are not black at all. So what I've told you so far is not entirely the truth. It's a pretty good approximation to the truth, but it's not actually fully the truth. And to get to that, let me discuss a concept which is a standard concept in physics, which is entropy. And I'm sure you've all heard the term. Entropy is essentially a measure of how disordered a system is. So a very low entropy state is a very ordered system. So this house of cards here is very ordered because it's very special. It's a very delicate configuration. And entropy measures the amount of disorder. So a high entropy state is something more like this, where all the cards are strewn around over the floor. In case you're wondering, this is my daughter, Luana, here. This is a high entropy state because it's very disordered. Well, Luana's not disordered. Well, no, she is disordered, but kids are disordered. So on that note, as I'm discovering, so the first law of parenthood is that disorder never decreases. Things only get worse and worse. Your life gets more crazy and more disordered. And this is essentially a fundamental principle of physics, which is called the second law of thermodynamics. And so entropy is the measure of disorder, and entropy never decreases. It only ever increases or stays the same. And that's a fundamental law of physics that we believe to be true. It was it's well tested, and one of the great developments of 19th century physics that we believe to be true. Now, when we think about the second law and black holes, we have a problem. And this problem was essentially pointed out, well, Jacob Bekenstein was one of the people that thought about it, who was a PhD student of John Wheeler, who was the guy who coined the term black hole. And he pointed out a problem that black holes naively seem to violate the second law of thermodynamics. Now, how is that? So imagine we take a bucket of water. You can imagine the water is hot or cold, it doesn't matter, but it's not at absolute zero, so it has some temperature. Then the bucket of water will carry some entropy. There'll be some intrinsic disorder due to the Brownian motion of all the atoms in the water that give it temperature. And now imagine that bucket of water falls into the black hole. If you put it too close, it falls into the black hole. And now the bucket of water has disappeared. But I told you that every black hole is specified only by its mass and its charge and its angular momentum. And let's assume the bucket has no charge and no angular momentum. Then all that's happened is that now we have a black hole with bigger mass. Mass is conserved, but the black hole is bigger mass, including the mass of the bucket of water. But now the entropy of the bucket has disappeared, because all we see is a black hole. And so we had a system where we have some entropy in the bucket of water, and the entropy has disappeared. And that contradicts the second law of thermodynamics, because it seems that the entropy has decreased in that process. Unless, of course, the black hole itself has entropy. And that was what Bekenstein suggested. And his main motivation was a theorem proven in 1971. It's called Hawking's area theorem by Stephen Hawking. And Hawking's area theorem basically says that the surface area of the horizon of the black hole, this special surface, which defines the point at which the escape velocity is essentially the speed of light, and so light can't escape from that point. And he proved that the surface horizon of black holes always increases. Now, his proof was more sophisticated, but I've given an elementary proof. Let's suppose we take two black holes, black hole 1 and black hole 2 of mass m1 and m2, and imagine they collide with each other. They'll combine into one big black hole. Now, the area of the black hole is proportional to the square of the mass of the black hole. So initially, we have an area 1, which is proportional to m1 squared, and area 2, which is proportional to m2 squared. But when they combine, the masses add up. But then the areas don't add. The areas go like the square of that sum, which is always bigger than the sum of the areas. And so that is essentially what Hawking's area theorem says, that the area always increases through the dynamical process of the black holes, in this case, the black holes combining together. The area, the final area of the combined black hole is bigger than the sum of the original areas. And Bekenstein suggested that that means that area of black hole has something to do with entropy. Because the second law of thermodynamics says that the total entropy of a system always increases or stays the same. It never decreases. Entropy always increases. Disorder always increases. Hawking's area theorem says that the total horizon area of all black holes always increases. It never decreases. It always increases or stays the same. So Bekenstein's conjecture was a very simple one, in the sense that the area of the black hole somehow measures its intrinsic gravitational entropy. And maybe this is the resolution of where the second law of thermodynamics was breaking down. But then there's a problem, because if black holes have entropy, then that means they're like thermodynamic systems. They must also have temperature. In other words, a black hole must be hot. Now, a hot thing, you expect to radiate heat. But that's impossible. A black hole simply can't radiate heat because it's black, right? Because the whole point is that it can't emit radiation because the terminal the escape velocity is bigger than the speed of light. However, that's not true. And the missing ingredient in this calculation is quantum mechanics. Einstein's theory of general relativity is a completely classical theory, and it doesn't take into account the other great revolution of 20th century physics, which is quantum mechanics, which of course comes from Planck, and then the early work by Planck, and then Heisenberg and Schrödinger and Dirac and many other people. And the resolution to this is that we really have to understand black holes, or at least the matter around black holes as quantum mechanical, because we know that quantum matter really satisfies the rules of quantum mechanics. And this was the trick to the resolution. And in fact, Hawking proved that Bekenstein was correct. He went away and he did a calculation, and he showed that the black holes indeed do have temperature, which I'll explain in a second. And he was able also to calculate the entropy of the black hole and show that indeed it was directly proportional to the area, as Bekenstein had suggested. And the way it was proportional depended on Planck's constant, which is the fundamental constant that determines how quantum things are, the strength of quantum mechanical effects. And so this was a great discovery. And that meant that black holes really were radiating hot objects. And we call that radiation Hawking radiation now, because Hawking was the one who really first did that calculation. And his picture is that those same quantum fluctuations that Claudia talked about last week that are responsible for sorting the cosmological constant, those same quantum fluctuations whereby particles and antiparticles are created all the time in the vacuum, that goes on for matter around around a black hole. But what happens is that every so often, one of the pairs of those produced particle-antiparticle pairs falls inside the event horizon, falls inside the black hole, and just becomes part of the bigger black hole. The black hole mass increases by the particle mass that falls in. And then the other particle can run out to infinity and look like radiation. And what Hawking showed is that, in general, the particle that falls into the black hole effectively has negative energy, so that the black hole actually decreases in mass. And the particle that then escapes out to infinity has to have positive energy so that the total energy change is the same. And that looks like Hawking radiation. And so the picture is that the black hole actually radiates away part of its mass at a specific temperature, which we now call the Hawking temperature, which is related to the mass of the black hole. And so this fit together the story. Indeed, Bekenstein was exactly right that black holes really do have entropy. They really do have some kind of disorder. They're thermodynamic hot objects, not very hot. The temperature is incredibly low for astrophysical black holes. But nevertheless, they do have a temperature at which they are radiating, and which we now call Hawking radiation. So this resolves the second law of thermodynamics. So let's go through it again. So take a bucket which has entropy, and it falls into the black hole. What happens is that then you just have a black hole, but the mass of the black hole is bigger. And the mass of the black hole is bigger sufficiently such that the entropy, which goes like the mass squared, is increased more and so that the entropy of the new black hole is actually bigger than the entropy of the original black hole plus the bucket of water. And then what happens is that the black hole starts to evaporate by Hawking radiation, and the black hole actually gets smaller because it loses mass. So that means that the black hole loses entropy, but then thermodynamics, the second law of thermodynamics, is still true because the radiation, the Hawking radiation that the black hole emits, itself carries entropy, and the entropy of the Hawking radiation is even more than the loss of entropy from the shrinking of the black hole. And so the whole system, the whole closed system, entropy always increases. And so in this sense, black holes preserve the second law of thermodynamics once you take into account the fact that they have entropy and they really do radiate.
Are there similarities between the time-space singularity and the almost infinite density prior to the Big Bang?
Yes, very much so. So it's the same type of singularity. In fact, they're both what we call space-like singularities. So what happens as you go inside of the black hole, actually space and time switch around, and so the singularity of a black hole is actually somehow in your future at a given time. But it's very much like the singularity of the back in your past, which is the Big Bang singularity. So if we understand what happens at the Big Bang, how the singularity gets resolved there, it'll actually tell us something about the singularity inside the black hole. At present, of course, both are difficult problems, but they're very much the same.
As far as the black hole, you're showing unidimensional, but is it multidimensional? In other words, if you come in from the back door, will you get the same effect?
If you have a theory of with extra dimensions, then you can have black holes in the extra dimensions as well, which can look like black holes in our 4 dimensions. So you can have things like a black string, which in our 3+1 dimensions looks like a black hole, but it extends into the extra dimension as like a string-like object. And there are all sorts of weird and wonderful extensions of the black hole idea to higher dimensions.
So basically, no matter what direction you're coming from, it's going to be, the matter will be sucked in.
Right, that's right, yes. It's always a black hole in the higher dimensional picture, yes.
Dark matter and dark energy. You're saying the black hole, under all circumstances, is always going to continue to grow. Is that because it's also picking up the dark matter and dark energy, which makes up most of the universe anyhow?
Astrophysical black holes have accretion disks around them where they're basically absorbing the matter or dark matter and around them visible matter all the time. And so they could actually be growing. So the Hawking radiation is an idealized situation. If there's no matter around the black hole, then the black hole would actually will get smaller because it'll radiate away its energy. But in astrophysical systems, the black hole tends to actually increase in size because there's matter around that it's sucking in all the time.
My understanding of the production of virtual particles is it has nothing to do with nearby mass. In fact, last week speakers said that they could be formed in a total vacuum.
That's right.
Now, if you had a pair of virtual particles forming within the event horizon of a black hole, nothing would ever escape. But it looks like, you know, from your illustration and from my understanding of Hawking radiation, that these are formed outside the horizon in basically normal or comparatively normal space, and would therefore have no connection with the black hole. So if particle A falls into the black hole, it just increased its mass by that amount. And if particle B goes flying across the universe, it does so with no connection whatsoever to the black hole. So how in this exchange does the black hole possibly lose mass?
So because the particle that goes in is typically one with negative energy. So these pairs so you have to conserve energy. So it's true that we have this picture that in the vacuum all the time we've got quantum fluctuations and antiparticle pairs being produced. But total energy is conserved. So effectively what's happening is that the particle going in has negative energy, which then decreases the mass of the black hole, and the one that escapes out has positive energy. And so the total energy is conserved in that process. It's a little subtle effect. I mean, that, of course, is an extremely simplistic explanation, and that's not what Hawking did. But in terms of that pictorial representation, that's the best we can say.
The second law of thermodynamics, I was under the impression that pertained to closed systems. Would the black hole be a closed system or an open system?
So the black hole itself is an open system, but in that representation, the closed system is essentially the black hole and the whole universe around it. And in my particular universe here, I have only one bucket of water and the black hole, and that's the closed system. And then that evolves, the bucket falls in, and then you just have one black hole in the whole universe. And then the black hole starts to emit radiation, and the closed system is then the black hole with the radiation. Yeah. But you're absolutely right, it applies to closed systems.
The particle and antiparticle virtual pair are entangled when they're made, and then one disappears. What happens to the wave function of the other one?
So you've hit you hit spot on exactly the right point. In fact, they really are entangled, and actually one picture, you can actually think of the entropy of the black hole as something to do with the entanglement entropy between the particle that goes the particle that goes out and inside. So I'm not sure I can answer that question because it's a very that's really ongoing research, understanding how the entanglement of the Hawking radiation plays out in the black holes. But that's connected with an important fundamental paradox associated with black holes that Hawking pointed out, which is the information loss paradox. And so he was worried that precisely because of that fact, once because once the entangled particles disappear inside the black hole, then you lose information on that particle. And so somehow you've lost the entanglement, and that looks like a loss of information, and that looks like a contradiction with quantum mechanics. I'm going to talk about a somewhat strange and bizarre idea, but one that is very profound and may explain many of these features. And this is the idea of holography, or the holographic world. And here you see a picture of a bunny rabbit trying to do the impression of a shadow hand on a wall, and which is somehow a representation of the holographic idea. And so what is this idea? So we've essentially reached at some level a failure of Einstein's theory. We know that the singularities themselves inside a black hole and at the Big Bang represent a failure of Einstein's theories. We don't know what happens there. But there's also this weird issue of trying to understand the entropy of a black hole. Now, Ludwig Boltzmann, who was the one who probably most contributed to our understanding of entropy and essentially developed the framework of statistical mechanics, which is the microscopic description of thermodynamics. On his tombstone, there's a famous equation, which is what he's most famous for, is that the entropy of a dynamical system, which is a measure of disorder, is essentially proportional to the logarithm of the number of fundamental number of different configurations, microscopic configurations that could make up a given macroscopic state. So the idea is that any object that has entropy could really be made out of lots of different microscopic configurations that look at macroscopic scales, look at large scales, basically the same. And W essentially counts the number of those different microscopic states that can make up that macroscopic configuration. And that essentially measures the amount of disorder. So the entropy gets bigger. There are more different ways the system the more different microscopic states the system can be in, and that's a measure of disorder. And so this fact that that black holes have entropy tells us that they really must be complex systems. We know that the entropy is a measure of disorder. So a black hole, which I told you in the first section was really this kind of perfect, unique object which was specified only by its mass and charge and angular momentum, that can't be quite true. Black holes have entropy, and therefore they must actually be very disordered systems. And in fact, they have a very large entropy typically. And the number of microstates, according to Boltzmann's formula, that would go to make up the black hole is the exponential, because there's a logarithm in that formula, the exponential, which makes it a very big number, of the area, which of course determines the amount of entropy, divided by 4 in units of the Planck length, which is the length at which quantum gravity comes in, which is about 10 to the minus 33 centimeters. Now, for typical black holes, an astrophysical black hole, the area over 4 times the Planck length squared is already a gigantic number. And the number of microstates is the exponential of that gigantic number. So essentially, it's just an incredibly gigantic number. And a black hole must be really some microscopic system which is made out of these gigantic number of microstates. And general relativity provides us with absolutely no clue to what these fundamental microscopic degrees of freedom are. And so that gives us the picture that according to Boltzmann, Einstein's theory of relativity is really just the thermodynamic description, thermodynamic macroscopic description, coarse-grained description of large-scale stuff. So it describes black holes, but it doesn't describe them perfectly. It doesn't describe the microscopic physics of a black hole. It just describes what typical black holes look like if I average over all that microscopic physics. But the fact that they have entropy tells us that there should really be some more fundamental, what we call a statistical mechanics microscopic description of that black hole. So the fundamental question here is, what is that microscopic description? And to some extent, this is a major feature of ongoing research in the physics of black holes. So now let me sort of point you in a direction of one type of idea that may resolve this. So entropy, typically you expect to scale with volume. So let's take up our bucket of water again. Let's imagine that bucket has some entropy S1. So S1 just measures the entropy according to Boltzmann's formula of that bucket of water. And take a second identical bucket. If the identical bucket has the same amount of water in, then that bucket will also have entropy S1. Now let's take those buckets together and put the water in a bigger bucket, which is twice the volume, so we can fit the water in. And we do this in a gentle way, which physicists call adiabatic, without disrupting the water too much when we do this. Then the total entropy of that new system will be twice the entropy of the original system. And the total volume of the water will be twice the volume of one of those buckets. And so that tells us that entropy for water, for a bucket of water, we expect to scale with the volume of that water. But the entropy of a black hole scales with area. That's what the Bekenstein-Hawking result said. The area of the horizon of the black hole, this surface at the Schwarzschild radius, we calculate that area, and Bekenstein-Hawking formula tells us that the entropy is actually proportional to the area. So the number of microstates of a black hole is determined by its area and not by its volume. And this has led to a remarkable idea, which is the idea that could be phrased as holography, or the world as a hologram, which goes back to the ideas of the Nobel Prize winner Tuft, and also Susskind, Lenny Susskind, who pushed the idea, who took very seriously this idea. And the idea is that, imagine that the world really wasn't 3 + 1 dimensional, so there weren't 3 dimensions of space and 1 in time. Imagine that there was only 2 dimensions of space and 1 of time. So there's really only 2 dimensions of space. Then what we call volume in 2 dimensions would just be obtained if we have, in 2 dimensions, 2 space dimensions, we can't have a cube. The best we can have is a square. If we want to compute the volume, the best we can do is multiply the length of this side and the length of this side. But from a point of view of 3-dimensional world, then that is just the area, because we're just multiplying 2 directions together, but we know there's really a 3rd direction. So the volume in a universe where there's only 2 space dimensions is the same as the area in a universe where there's 3 dimensions. So we know that the number of microstates of matter, like the bucket of water, typically scales like the volume. And the volume in a 2 + 1 dimensional space scales like the area. But the entropy of a black hole in 3 + 1 dimensions also scales like the area. So there's this weird connection that effectively the number of microstates of matter in 2 + 1 dimensional space-time, so in a space, and when we only have 2 space dimensions, the number of microstates of a bucket of water with 2 space dimensions is the same as the number of microstates of a black hole in 3 dimensions. And this is the remarkable idea, because we're mapping together the bucket of water in a different number of space dimensions than the black hole. In some sense, gravity and the theory of gravity, although we're talking about gravity in 3 dimensions, one of those dimensions somehow doesn't count in computing the entropy. Now, this was a somewhat speculative idea when originally proposed, but then it got a realization after the development of the idea of D-branes in string theory, where branes are extended objects. If you have a theory with multiple dimensions, then our universe could actually be constrained to some kind of membrane-like surface living in those extra dimensions, which I think Claudia may have talked about before in the context of extra-dimensional models. And in the context of string theory, these are called D-branes, but we can call them membranes. They're just surfaces, sheets of matter living in extra-dimensional spaces. And so this has led to the picture that maybe our universe, our 3 + 1 dimensional universe, maybe is just living on a brane in some higher dimensional geometry. Now let's think about the bucket of water for a second. So that bucket of water, what is it made up of? It's made up of atoms. Those atoms got electrons and neutrons and protons. Those neutrons and protons themselves are made out of quarks. So let's think about the matter localized on a surface, now a brane, but the surface, this brane, instead of being 3 + 1 dimensional, so instead of having 3 space dimensions, it just has 2 dimensions, like the picture. And imagine 2 quarks sitting on that 2-dimensional membrane. Then, now we imagine, in the context, the brane picture really came out of string theory, so let's imagine we have a string. You can think of a string extended, you can think of the quarks as sitting in the endpoints of a string, which is extended out into the 3rd dimension. So here we have a 2-dimensional brane geometry with quarks sitting on that surface, and then the string extends out into the 3rd space dimension. Now, one thing we know about strings is that there are excitations on the string that are associated with gravitational waves. And this is one of the reasons people believe that string theory can act as a quantum theory of gravity, is because one of the excitation modes along that string is a gravitational wave. It's a graviton. There's a particle associated with that called the graviton, which can propagate the gravitational force. And if you want to compute the force between those two quarks on that sheet, I can actually do it by computing essentially the energy of that string. So if I want to know about, so imagine I'm only confined to that 2 + 1 dimensional surface, and I just want to know the force between those two quarks. I can perform the calculation of that force either directly in the theory of the quarks that lives on that surface, or I can map that into a theory of the string, which is really a theory of gravity living in the extra dimension, which is really our third dimension, the one in which we're living, our 3 space dimensions. And there you have a gravitational theory, and you can compute the force between the quarks by computing the energy of the string and varying that with respect to the distance between the two quarks. So that means there's two ways to do this calculation. There's two different pictures. There's effectively a theory that just describes what's going on for the quarks sitting on the surface, or there's a gravitational theory in the bulk. And they both give the same information, so there's a connection between those two things. And this is what led to what's called the ADS-CFT correspondence, which is essentially a full realization of this idea of holography. The idea is that, a black hole here sitting in a bulk, imagine that our three-dimensional world is surrounded by a two-dimensional boundary, which is the sphere here. And so we have gravity acting in the bulk, gravitational degrees of freedom associated with the black hole. But we know that the entropy of the black hole is somehow counts in the same number of degrees of freedom as the entropy of a theory of matter which lives in one lower dimension. And so the picture that Maldacena, who developed the ADS-CFT correspondence, gave is that there are two ways to describe the gravitational system, two ways to describe the black hole system. Either the picture of gravity and the black hole, which is in a three-dimensional space, or there's a completely equivalent theory, which is essentially the holographic projection of that theory. We can think of the surface as being somehow a hologram of all the physics inside the bulk. And I can compute physics going on this surface. I compute what goes on, and that tells me about what's happening in the bulk. And all the information contained in the bulk gravitational theory is somehow encoded on the surface, on a 2 + 1 dimensional surface. And this is why it's called holography. The idea is that a two-dimensional holographic projection of a three-dimensional physics can contain all the information. So if you took some two-dimensional holographic photograph, from that photograph, I can reproduce all the information about the three-dimensional bulk geometry. But the remarkable thing is that the bulk theory is a gravitational theory, whereas the surface theory is a non-gravitational theory. It's just a theory of quarks, or it's a theory of buckets of water, or whatever that matter is. So it's a purely non-gravitational theory that lives on the surface, is equivalent to a gravitational theory living inside the bulk. So in some sense, gravity theories in 3 dimensions are equivalent to non-gravitational theories in 2 dimensions, or gravity theories in 5 dimensions are equivalent to non-gravitational theories in 4 dimensions. And this connection has led to many useful and deep understandings of the physics of black holes and the entanglement entropy associated with them, and maybe one of the most useful ideas in terms of understanding really what happens, why black holes really do have entropy and what the microscopic physics is. So what we've been led to is essentially the idea that maybe we have to completely rethink our picture of gravity. Newton said that gravity was a force, that force acted at a distance. Einstein said, no, that's not right. Gravity is really somehow the curvature of space-time. But then this holographic picture says, well, actually, maybe that's not even right. Maybe there isn't really a gravity at all, and maybe there isn't really a third dimension at all, that somehow a theory of gravity in 3 dimensions is really equivalent to a theory without gravity in 2 dimensions. And I can describe everything that's going on for gravity in a theory where there's no gravity at all. And that's the idea of holography. So that's an incredibly, I mean, it's a crazy idea at some level, but it's also a beautiful idea, and it's one of the ideas that really makes us understand why black holes do have entropy in the entropy scales with the area and not with the volume. And the hope is that it will really lead to a profound profound revolution in our understanding. So in this picture, the idea is in fact that by mapping a gravitational theory like general relativity onto the theory in 2 dimensions, which is non-gravitational theory, that non-gravitational theory doesn't have all the problems associated with singularities and so on, because there's no gravity there. And so maybe we can use that theory to understand what happens at a singularity. And the idea is it's really a microscopic equivalent description of what's going on.